Quantum computing, second lecture. Let's continue where we left off. So, reiteration that we will introduce the basic terminology and concepts that will be used throughout the course, setting the stage for deeper dive into the mathematical and physical principles underlying quantum mechanics. Overcoming the obstacles are decoherence, error correction. Example is keeping qubits stable. Let's look into decoherence and later error correction with one example each. In reality, these terms, decoherence and error correction, are the areas of research in their own accord. Decoherence is one of the biggest challenges facing quantum computers, and it's the reason why building a practical quantum computer is so incredibly difficult. Remember, we discussed about qubits, so how qubits can exist in superposition, being both 0 and 1 at the same time. That's a great question. Well, this delicate quantum state is extremely fragile and can be destroyed by almost anything in the environment, such as heat, vibrations, electromagnetic radiation, or even the stray particles in the air. When a qubit interacts with its surroundings, it loses its quantum properties and decoheres, collapsing from the useful superposition state into just a regular 0 or 1, like a normal bit. It is similar to trying to balance a pencil perfectly on its tip. Theoretically possible, but the tiniest breeze, vibration, or movement will knock it over. Once decoherence happens, the quantum computer loses its computational advantage and starts making errors. This problem, or the problem, is that decoherence happens incredibly fast, often within microseconds or millionths of second, technically, which means quantum computers have only a tiny window of time to perform their calculations before the qubits decohere and the information is lost. To understand how serious this problem is, imagine you're trying to solve a complicated math problem, but your pencil and paper keep disappearing every few seconds, forcing you to start over from scratch. That's essentially what decoherence does to quantum computers. This is why quantum computers must be kept in extreme conditions. They are typically cooled to the temperatures near absolute zero, as mentioned earlier, colder than the outer space, isolated in vacuum chambers, and shielded from any electromagnetic interference. Scientists also use something called quantum error correction, where they use multiple physical qubits to represent one logical qubit. So if some qubits decohere, the others can maintain the information, kind of like having backup copies. For example, IBM's quantum computers need to maintain their qubits around 0.015 degrees above absolute zero, that is about minus 273 degrees centigrade, which requires massive refrigeration systems that look like giant chandeliers. Despite these extreme measures, current quantum computers can only maintain coherence for about 100 microseconds before errors start piling up. This means that until scientists figure out how to extend coherence times or develop better error correction, quantum computers are limited in how complex their calculations can be. So that's the example here of keeping qubits stable. Quantum error correction, as mentioned earlier, importance for error correction. That's where we keep the backup qubits. Example is surface codes, and we'll go into this topic in a little bit more depth in the upcoming lectures. Types of quantum computers: superconducting, trapped ions, topological qubits, IBM superconducting qubits. I would suggest you to conduct a little research on all of these four and see what you grasp from the available information. Programming quantum computers: QI Scikit, Cirq, QUTIP. Example, writing a simple quantum program. So you can go on Google Colab and you can use these kits to write a very simple program or quantum algorithm to see how programming happens in quantum computers. But before we go to the programming, we will be needing to learn the quantum automata in a little bit more depth before even we jump in and start coding anything. Speed comparisons. Now let's look into this in a little bit more depth. Exponential speedup is the concept that makes quantum computers truly revolutionary. For certain types of problems, to understand what exponential means, imagine you're trying to guess a 4-digit password. With each additional digit, the problem does not just get a little harder, it gets dramatically harder. A 4-digit password has 10,000 possibilities, but a 5-digit password has 100,000 and 6-digit has 1 million. The difficulty multiplies by 10 with each new digit. For classical computers, some problems grow in difficulty so fast that even small increase in problem size make them impossible to solve in any reasonable time. A problem that takes 1 second with 10 pieces of data might take 1000 seconds, and 20 pieces 1 million seconds, and 30 pieces and longer than the age of universe with 100 pieces. Quantum computers, however, can achieve exponential speedup on certain problems, meaning they can solve them in a time that grows much more slowly, perhaps taking only seconds or minutes for problems that would take classical computers billions of years. The most famous example of exponential speedup is factoring large numbers, which is the problem of breaking a big number down into smaller prime numbers that multiply together to create it. For instance, if I give you a number 15, you can quickly figure it out that it is 3 multiplied by 5 or 3 times 5. But what if I give you a number that is 617 digits long? A classical computer would have to essentially try dividing by every possible combination of prime numbers, and the number of possibilities grows to astronomically large that even the world's most powerful supercomputer would take millions of years to find the answer. In 1994, mathematician Peter Shor invented a quantum algorithm, as we discussed previously, now called Shor's algorithm, that can factor these huge numbers exponentially faster. A problem that makes a classical computer billions of years could potentially be solved by a large enough quantum computer in just hours or days. This matters enormously for internet security because most of our online encryption, also known as RSA encryption, relies on the fact that factoring huge numbers is nearly impossible for classical computers. If someone has your bank's public encryption key, which is a huge number, they would need to factor it to crack the code and steal information, something that's currently impossible. But once powerful quantum computer exists, they could break this encryption, which is why cybersecurity experts are rushing to develop new quantum resistant encryption methods before that day arrives. That's also known as quantum day, by the way, just FYI. What quantum computers cannot do? Not a replacement of classical computers. The example is poor performance when everyday tasks for now. Combining classical and quantum machines, hybrid algorithms, quantum assisted optimization. But before I jump into this, let me find you the real example that what quantum computers cannot do. Despite all the excitement around quantum computing, there is a lot that quantum computers cannot do today. And some things they will never be able to do better than regular computers. First and foremost, quantum computers are terrible at everyday computing tasks that they cannot browse the internet, play video games, edit documents, or stream videos. These tasks are actually much better suited for classical computers, which are highly optimized for sequential processing and general purpose computing. Current quantum computers are also extremely limited. Today's best quantum computers have only a few hundred qubits, and they suffer from very high error rates, meaning they give wrong answers frequently. They can only run programs for microseconds before decoherence destroys their quantum states, so they can't handle long, complex calculations yet. Quantum computers need massive, expensive infrastructure. They must be kept at temperature nearly absolute zero, as mentioned earlier. Even for the specific problems where quantum computers should theoretically excel, like breaking encryption or simulating molecules, today's quantum computers are not powerful enough to outperform classical supercomputer on practical real-world versions of these problems. Scientists estimate we'll need quantum computers with thousands or even millions of error-corrected qubits before they can solve truly useful problems, and we're still many years away from achieving that goal. That does not mean that we should not learn this technology, because computer science was invented by the programming was invented by Ada Lovelace. Check out who Ada Lovelace was in your learning time to figure out that there was absolutely no computer. Then Charles Babbage was another person that was in standard computer science, considered as the godfather of the modern computers. So now let's look into combining classical and quantum algorithms. These are technically hybrid algorithms heading face to face with quantum assisted optimization. Hybrid algorithms are a clever way to get the most out of today's limited quantum computers by combining them with regular classical computers. Since quantum computers are still too small and error prone to solve entire problems on their own, scientists have developed algorithms where the classical computer does most of the heavy lifting and only sends the hardest part to the quantum computer. Think of it like a team project where each person does what they are best at. The classical computer handles all the routine calculations, data management, and optimization tweaks, while the quantum computer tackles just the specific quantum tasks that it excels at, like exploring multiple possibilities simultaneously. The two computers work back and forth in a loop. The classical computer sets up a problem and sends it to quantum computer. The quantum computer processes it using superposition and entanglement, then sends the results back to the classical computer, which analyzes those results and adjusts the problem for the next round. This approach is called variational quantum eigensolver, or also known as VQE, and quantum approximation optimization algorithm, or QAOA, allows us to use today's noisy, imperfect quantum computers for practical applications rather than waiting decades for perfect quantum computers to help us. Quantum assisted optimization helps solving problems where you need to find the best solution for millions or billions of possible options. And it is already being tested in real world industries. Optimization problems are everywhere. Airlines need to figure out the most efficient flight schedules. Delivery companies want the fastest routes for their trucks to follow. The manufacturer need to organize production lines to minimize costs. A great real life example is Volkswagen's traffic optimization project in Lisbon, Portugal. The company used a quantum computer to optimize the bus routes in the city, trying to figure out the best paths for buses to take so passengers spend less time waiting and traveling. The problem is incredibly complex because you have to consider traffic patterns, passenger demand at different times, bus capacity, and thousands of possible routes with so many variables. The number of possible solutions is astronomical. Volkswagen used a hybrid quantum classical algorithm where the quantum computers explore different route combinations simultaneously using superposition, while the classical computer handled the practical details like current traffic data and scheduling constraints. Although this is still experimental, the quantum assisted approach found better solutions faster than purely classical methods, potentially saving time and fuel with improving service for the passengers. Similar approaches are being explored for optimizing investment portfolios, designing new materials, and even planning radiation treatment for cancer patients. So, hope this has given you some understanding of the merger. The ethics in quantum computing, the security risk is one ethic that we have to look at. Job displacement is another one. Impact on cybersecurity jobs, as mentioned earlier about the RSA cybersecurity. The future of quantum internet, secure communication networks, and quantum key distribution. The quantum key distribution by itself is a humongous topic for us to look into. Industry adoption, who's using quantum computing, finance, healthcare, logistics, as mentioned earlier. Example is JP Morgan Chase's quantum research is working in the arena of finances and logistics and all associated with where the transaction happens in terms of monetary transactions. Learning quantum computing, Q Sharp, Qiskit, Penny Lane. Example is Hello World in Qiskit. I would suggest you to conduct a little research on this on your own so you understand how Hello World is written, and you can use Google Colab because that's the best bet I have found so far, which runs the IBM's quantum libraries quite efficiently. Assessing quantum computers or accessing quantum computers. Cloud-based quantum computing is available by IBM and Google. Example is AWS Bracket, and obviously Amazon is the one which is simulating quite a few of quantum computing services which are available to us. In healthcare, simulation protein folding, COVID-19 research was the first time when the quantum computing came to help the researchers, scientists. Portfolio optimization, as mentioned about JP Morgan Chase, risk analysis is the area where quantum computing can be extremely helpful. Optimizing supply chains, route and resource optimization, as we just mentioned about Lisbon, Portugal example, that is applied equally on the DHL's quantum projects. DHL is like FedEx for us in United States. The road ahead. Predictions for next decade. Scalable quantum computers. Let me share some predictions that I have been part of with several organizations who deal with quantum computing, such as Sandbox AQ. The road ahead for quantum computing is both exciting and challenging, with scientists like yourself and engineers like yourself working to overcome major obstacles while racing toward practical applications. The biggest challenge is scaling up. Today's quantum computers have a few hundred qubits, but we need thousands or even millions of error corrected qubits to solve truly revolutionary problems. This means developing much better quantum error correction techniques, extensive coherence times so qubits can maintain their quantum states for longer, and finding ways to correct and connect large numbers of qubits without them interfering with each other. Different companies are exploring different approaches. IBM and Google use superconducting qubits, tiny circuits cooled to near absolute zero, as mentioned earlier, while others like IonQ has been using the trapped ions, individual atoms actually, held in place by lasers. And still others are experimenting with photonic qubits using particles of light, or topological qubits, a more stable but harder to build type. Most experts predict that within the next 5 to 10 years time frame, we will reach quantum advantage or quantum utility, the point where quantum computers can solve practical real-world problems better than classical computers, particularly in the areas like drug discovery, material sciences, and optimization. So what? That's a great question. What excites you most about quantum computing? I definitely would like to hear from you in this case. Happy learning. We'll continue next week.